Hi everyone, and welcome to another Mathematics and High Energy Physics seminar at Physics Latam. Today we are happy to have Professor Taro Kimura, who will be giving 2 lectures on quantum geometry and algebraic aspects, supersymmetric gauge theories. Professor Kimura did his PhD at the University of Tokyo in 2012. Afterwards, he went for several postdoc positions at the Institute of Theoretical Physics at Paris-Saclay and Rinken in Japan. Currently, he is professor at the University of Bourgogne in Dijon, France. His research interests lie in theoretical physics and mathematical physics. In particular, he is interested in exploring quantum field theory and its mathematical aspects and applications. So we are happy to have him with us today. And next week, there will be the second and final talk. And I hope you enjoy. And I will leave it with you with Kimura-san.
Okay, thank you very much for the introduction, and it's very happy to join this seminar series, which is very nice. And today I'm going to talk about this title, this title, quantum geometric algebraic aspect of this supersymmetric gauge theory. So this subject is really quite broad, but for example, I just give one reference, which is this 2012, etc. So then if you're interested, so basically today's talk is roughly based on this review article. So okay. So then let me start with introduction, and then I will go through more details of this subject. So then, of course, if you have any questions, so anytime you can interrupt me anytime you want. Okay. So then idea of, okay, let me start with the idea of this talk. So then, okay, introduction. So, okay, so, okay, as this title suggests, so this is, we are interested in this supersymmetric gauge theory, but this is actually one very specific type of the quantum field theory in general. So then in general, so we are interested in this quantum field theory, so which is very universal method in theoretical physics. And the universal means that so it has very broad applications, starting from, of course, high energy physics, and also so astrophysics, cosmology, and also the condensed matter. So many applications. So from this point of view, so I think no one doubts this usefulness of this quantum field theory at this moment. And okay, so this, but of course, at the same time, this QFT is still very, difficult object in the sense that, for example, still for the moment, we don't have a rigorous mathematical foundation and so on. So then still kind of the heuristic approach, but we still have already have many nice interaction with the mathematics, for example, mathematical physics, etc. So then typically, so what we do for this QFT is that first thing is the perturbative analysis, perturbative approach. So this is the most typical approach. For example, in the context of QED, etc. So we have a very precise theoretical computation, which is of course consistent with very high precision experiments. This is an application of this high energy physics, but also in the condensed matter or statistical physics. So the technology of this quantum field theory to compute to discuss a critical phenomenon. So then we can compute critical exponents with very high precision, etc. But anyway, so this perturbative approach. So typically, so we assume that this is available for this weak coupling regime. Okay, so of course this perturbative approach is works very well, but we assume that this coupling constant is sufficiently small. Otherwise, this perturbation theory is not good enough. Okay, so anyway, so this perturbative approach is still very interesting and a very successful approach. But of course, we are also interested in more as a side of the quantum field theory. For example, let's say this non-perturbative approach. So sometimes this non-perturbative approach is necessary in the sense that, okay, for example, QED, so we have a great success. But for example, in the context of the QCD, so if you are interested in the core confinement, etc., so actually this perturbative approach is not sufficient to study such kind of phenomena. So the reason is that, okay, so this QCD and the this confinement, etc. So we should discuss the very strong coupling regime. So in that sense, standard perturbation approach is not, not applicable. So then typically, so in a strong coupling regime, so we need some alternative approach. Okay. And okay, but of course, if you can do the very generic non-perturbative analysis, of course, it's excellent. But at the moment, so unfortunately, we don't have a very generic kind of a non-perturbative approach. So in that sense, but of course, this non-perturbative approach actually quite depends on the situation. So in the sense that, for example, in order to discuss non-perturbative aspects, for example, we typically think about some additional symmetry or additional, constraint on the dimensions, etc. Yeah, of course, the constraint on the dimension, of course, is related to some symmetry structure. But anyway, so this in order to apply this non-perturbative approach, so we assume, okay, for example, having higher symmetry or some specific dimension, for example, 0 dimension or 1 dimension, lower dimension. So we have a relatively nice approach. So then in that case, sometimes we can do the non-perturbative analysis even for this strong coupling quantum field theory. Okay. So this is a very generic remark, but then what we do in my talk is that, okay, especially so we're interested in this supersymmetric gauge theory. So let's focus on this specific quantum field theory. So as this name suggests, so this is a the quantum field theory having supersymmetry and the quantum field theory for this gauge field. So this is supersymmetric theory. But okay, so why we study this theory is at the following. So actually, thanks to very high symmetry and structure, actually, so we have a very nice technique to deal with the non-perturbative structures. For example, we can discuss several non-perturbative properties like the dualities, or some, for example, exact results, and so on. So we have several couple of non-trivial non-perturbative aspects. So actually, for example, this duality is very interesting in the sense that duality typically changes our weak coupling regime to strong coupling regime. So then, of course, we are originally interested in strong coupling regime, but after this duality transformation, we can convert the system to the weak coupling regime. So then we can analyze, for example, the perturbativity. And another thing that I wrote here, exact result, is that, okay, typically, so we apply a path integral formalism to quantize gauge theory or quantum field theory in general. And in general, so this path integral is very, difficult to justify mathematically. But if you have a supersymmetry, sometimes we can justify all the process to derive the partition function. So that I will mention in my talk. But for example, if you have such higher symmetry, so we can discuss several non-perturbative aspects. Okay, so this is one of the reasons. Of course, this is supersymmetric gauge theory is a very specific type of QFT, but the lesson here will be also useful to any quantum field theory. This is our hope. Okay, so then this is our primary interest. So then with this supersymmetric gauge theories, what we will discuss. Actually, so this title, okay, in a title, for example, we have a word like quantum geometry and quantum algebra. So what is this? So the idea is the following. So I will explain later, but this supersymmetric gauge theory or related theory has a nice, for example, geometric characterization. For example, supersymmetric gauge theory having extended supersymmetry, we have a so-called subwritten theory, which is a very geometric characterization of this supersymmetric gauge theory. And okay, so then if you say okay, geometric approach, of course we think about some standard geometry. For example, I will give you the one example. So this supersymmetric theory has a geometric description using a so-called Riemann surface. So Riemann surface here, we said algebraic curve is some characterized as a algebraic curve. So then I will give a more concrete example, but so starting from the study of this supersymmetric gauge theory, so we encounter some algebraic curve, which is nicely described as a Riemann surface. And so this Riemann surface is characterized as some zero function, okay, zero locus of some algebraic function. So this is an algebraic function of x and y. So then for the moment, okay, Riemann surface, okay, if you study the Riemann surface in underground course, for example, this Riemann surface is associated to the meromorphic function or some complex function, etc. And okay, so but anyway, so this is a standard geometric object. But I will talk about some quantum version of this. Quantization, quantum version means that, okay, for example, this Riemann surface is characterized as using these two complex variables, x and y. But for example, the quantization in this context is that quantization means that, okay, originally we have x and y variable, but this is now replaced with some operator such that having a canonical commutation relation. Okay, so originally, so we have a standard variable x and y, which are commuting each other in the original setup. But okay, so the idea of quantization here is that replacing x and y with a non-commutative, say, operator value thing, with obeying this canonical commutation relation. So this is a quantization that I will discuss. Of course, this is motivated by the standard quantization scheme, I mean, canonical quantization scheme. But actually, this quantization of this Riemann surface, etc., it has a very natural, origin in the context of supersymmetric theory. Okay, so then from this point of view, for example, we can introduce a notion of a quantum curve. The naming here is that originally, so this Riemann surface is given as algebraic curve. So then that's why so we use a terminology like a quantum curve. So quantum curve is typically denoted like this, characterized like this, 0. Okay, I will give you a more precise description, but the idea here is that, okay, originally this algebraic curve, sigma is given by the zero locus of this algebraic function. But now at the level of the quantum situation, so x and y are now operators. So then in the sense that, okay, so operator 0 doesn't make sense. So instead, so we typically think about, okay, in the sense, h is promoted to the operator acting on some object. And actually, so recording the standard quantum mechanics course, so this is very analogous to the, okay, h is going to be the kind of Hamiltonian, which is a quantization of classical Hamiltonian, which acts on some wave function. So in that sense, a quantum curve is really analogous to the structure of the Schrödinger equation or this kind of quantization scheme. Okay, so this is just a very generic, but I will give you the more detailed and more example. So how we have this algebraic curve in the context of this quantum field theory, and also how we can get this quantum curve. And okay, so let me give you some example. But for example, typically, so this we have a so-called hyper elliptic curve. So which is a special case of this situation typically. So this is a degree 2 for y variable, but the degree is arbitrary for other x variables. In this case, this algebraic curve is called a hyperelliptic curve. And then quantization condition is now, okay, x hat is just a multiplication of x variable, as in the case of the standard quantum mechanics. But on the other hand, so in order to have a canonical computation relation, so this y hat should be some derivative with respect to this x variable. Okay, in order to have this canonical computation relation, so x hat, y hat takes this kind of form. So then, in this case, what is this quantum curve? So in this case, for example, this h, x, y hat acting on some wave function is written like as a so like this, and then a multiplication of something like this. Okay. So then in this context, from this hyperelliptic curve, so we have it's got the Schrödinger type differential equation. So this is actually this is Schrödinger type. For the so then in this context, the quantum curve is nothing but the Schrödinger type differential equation. So then actually from this Schrödinger equation, so we have a very lot of interesting physical quantities. So okay, so this is a first part. I mean, in a sense, what is this quantum geometry in my talk? And okay, so from this point of view, so this quantization scheme is also related to some quantum algebraic structure, in a sense that, okay, so just a remark here is that why this is also related to the quantum algebra. So one remark here is that, okay, so this sigma discussed here, Riemann surface or algebraic curve. This has, okay, this appears from this quantum field theory analysis, but this is also interpreted as a kind of as a phase space of classical integrable system. So, okay, so before the quantization, of course, this is a classical mechanics or classical system. And but now, okay, so we can, it turns out that this Riemann surface obtained here can be interpreted as some phase space of classical integrable system. So from this point of view, so if you quantize this object, so quantization, so of course, originally this is associated to classical integrable system. So then it's natural to expect a connection with a quantum integrable system. And also, okay, so but then, this quantum integral system, of course, this is a very nice family of quantum mechanical system. But of course, underlying, so we have a very interesting underlying algebraic structure, because in order to have a quantum integral system, so we have a typically infinity many commuting Hamiltonian, etc. But actually, so there's a nice algebraic object which controls all these commuting Hamiltonians. So then, in that sense, associated with quantum integral system, so we expect some underlying, some say quantum algebra. So then, in the context of quantum integral system, so we have a very interesting, typically infinite dimensional quantum algebras. Quantum algebra means that, okay, typically in order to discuss the symmetry of the physical system, etc., so we use Lie algebra or Lie group. But the quantum algebra is actually the extension of such standard Lie group or Lie algebra. So typically, so it's given by the Yangian or quantum affine algebra, or more even quantum toroidal algebra, etc. So we have many kind of the generalizations, but typically, so the idea here is that, okay, after the quantization of the classical integral system, so we have some correspondence to the quantum integral system. And at this moment, so we have actually some nice underlying quantum algebraic structure. So from this point of view, this quantization problem or this Riemann surface or algebraic curve, of course, this is interesting in the context of quantization of geometric point of view. But also we have a nice connection with some quantum algebraic structure. So then in my talk, I will make a connection with all these stuff, starting from some quantum field theory system, and also it's a connection to the algebraic structure, and also this quantum algebraic structure, quantum geometric and the quantum algebraic structure. So this is the aim of my talk. Okay. Okay, so do you have any question at this moment? Is it okay? Okay. So this is the introduction and the big picture. And then actually using this geometric aspect and algebraic aspects, so actually we can nicely characterize the non-perturbative aspect of this quantum field theory system. Okay, so then let me give you the plan of my talk. So the first part is, okay, kind of the warm-up, in the sense that I will discuss a bit of the matrix model. So I will explain why this matrix model is necessary to, as a kind of the warm-up of this project, this subject. And the second, I will discuss this 4D n equal to supersymmetric gauge theory. But I will also discuss its cousins. Okay, so the family of the similar systems. The thirdly, so it depends on my progress of my talk, but I will also discuss and generalize gauge series. Okay, so then let me briefly explain why we have this kind of structure, especially why we started this matrix model. So the idea here is that this matrix model has been studied a very long time. And the reason why is that actually, so this is very important in the sense that it's interpreted as a kind of the zero-dimensional QFT system, roughly speaking. I will discuss more detail, but because, okay, as I mentioned in the introduction part, in order to apply this, in order to study non-perturbative aspect or something, so for example, if you have a low-dimensional system, so typically, so we can have more techniques to discuss non-perturbative aspects. So actually, this matrix model plays a role of kind of zero-dimensional reduction of QFT. So in that sense, actually all these quantum algebra, quantum geometry, etc. So we can discuss this with this matrix model. So in that sense, this is a very this is a very nice toy model in this context. And then actually, so after studying this matrix model, actually, so we emphasize how this 4D supersymmetric gauge theory has overlap or has similarity with the matrix model techniques, etc. So actually, this conceptual, of course, is a very big jump from 0D to 4D, but at technical level, so we have a very similar structure. So in that sense, actually, studying matrix model very detailed is very important in my talk. So then the third part is generalized gauge theories. That means that, okay, second part, so I will discuss this 4D gauge theory. But the general gauge theory is that, okay, actually, so this kind of quantum geometric structure, algebraic structure can be also extended to the, for example, higher dimensional, much higher dimensional gauge theory, like the 60 or 80, or more even generic in the sense that starting 8-dimensional, but only thinking of the 4-dimensional subspace, etc., and its combination intersection. So we can study even much complicated situation. But in this case, even in this case, we can discuss a similar quantum algebraic or quantum geometric structure that will be discussed in the first and second part of my talk. Okay. So then, okay, so let us start with this first part, which is a matrix model. Okay, so this is a as I said, a zero-dimensional quantum system, but it has a very similar structure to the, for example, 4D M-2 supersymmetric case theory. Okay, I will explain why this is the case. So then, what is a matrix model? So the matrix model, of course, there are many nice articles. But let me just pick up my one of the reference. Many things, but 4430. So this is a review article written with my colleagues. Of course, we have many others. Let me just pick up one of these. Okay, so then let us study the matrix model. So first of all, let us discuss what is this matrix model. So then matrix model is, of course, the model of the matrices, but in which sense? So let's think about some certain typical Hermitian matrices of size n. Let's think about the Hermitian matrices of size n. Okay. So then in this for these matrices, so what we think about? Let's think about the model of this Hermitian matrices, which is given by the analog of the path integral formalism. Let's define the partition function. Given by, it's denoted z, dn, exponential of, okay, for the moment, let's put n trace vn here. So let's discuss this kind of integral. And now this trace of b is, which is, this is called a so-called potential term, where this trace of v of n is, okay, equal 1 trace of m2 k. So in this context, tk is basically the couplings. Okay, let's think about this kind of integral. So then in this case, so okay, precisely speaking, we should specify what is this dm, I mean the integral measure of this corresponding Hermitian matrix. And for example, this dm is typically basically this okay, decompose, okay, because this is a Hermitian matrices. So this is given like this, typically diagonal component and the off-diagonal component. But since this is a Hermitian matrices in general complex valued, so then we have a real part and also imaginary part of diagonals. So this is just a flat measure of this Hermitian matrices. And then okay, so okay, this is just integral matrices. And then what we can discuss here. The first thing is that actually the symmetry of this system, which is very important. So actually this integral is invariant under the following transformational matrix, which is M2 U M U dagger. So where this U is a unitary matrix. Okay. So this is at least this is clear for the so-called this trace term, potential term, because this trace of matrix power, of course, this is invariant under this kind of unitary transformation. That's fine. And also, it's not so much trivial, but this under this transformation, this matrix measure is still similarly invariant. So this is related to, for example, this unitary matrix determinant is absolute value 1. So then in that sense, there's no non-trivial Jacobian under this transformation. Okay. So this is, okay, so from this point of view, this matrix integral is invariant under this unitary transformation. So here, the remark here is that actually, so this is one of the reasons why this matrix model is interpreted as a zero-dimensional reduction of quantum field theory. Actually, so this is so remnant of gauge theory, gauge symmetry, in a sense that the standard gauge symmetry, okay, so if you have a gauge field, so if you think about the gauge transformation, so this is actually a transformation in adjoint representation. So in that sense, okay, of course, there's no differential term, etc. But similarly, this matrix model is invariant under adjoint action of this unitary transformation. So in that sense, this is a zero-dimensional reduction of gauge theory. So this is one of the reasons why. So we can say we can interpret the matrix model as a zero-dimensional reduction of this gauge theory. Okay. So in that sense, this unitary transformation is interpreted as a kind of the gauge transformation in this context. Okay. So then, now it's okay. So we have this kind of symmetry, but how we can use this kind of symmetry to solve this problem? So so then typically, so what we do with this symmetry is the following. So actually, so this symmetry means that we can change the basis of this Hermitian matrix. Or otherwise, we can say that we can choose a nice or otherwise a convenient basis to discuss this problem. So for this purpose, so let's think about, so actually we can discuss this diagonalization. I mean this, so let's choose a basis which diagonalizes this Hermitian matrix. So in the sense, M is written as follows. So now this big X is a diagonal matrix of this form. Okay. So of course, in the beginning, so we have integral matrices, but of course it's very convenient to discuss just with eigenvalues or eigenvectors. So in this context, this diagonalization, so I wrote this M as a U, X, U dagger. X is eigenvalues, and in this context, U is corresponding to the union of the eigenvectors. So this kind of separation variable is very important. And then the question is, nice. So if you diagonalize, so we have just eigenvalues and eigenvectors, but then partial function looks like what? Okay, so after this diagonalization, we can, I skipped a bit detailed computation, but we have this kind of structures. Integral over dx. But this is a integral over the eigenvalues minus n e of xi. And then we have this additional contribution, and also integral over this part. Symbolically write this way. Okay, so I think it's better to compare this original expression. So the original expression is on the top. So we have this partial function as the integral over the Hermitian matrix. Yeah. And on the bottom, so we have an integral in terms of eigenvalues and the eigenvectors. So U basically correspond to the eigenvectors. So then we have an additional contribution compared to the first expression. For example, this part actually appears as a Jacobian, because we changed the variable from the matrix element to the eigenvalues and eigenvectors. So then actually we have a non-trivial contribution Jacobian in this case. Okay. And then, okay, so let me comment each term. The meaning of each term is that, okay, so we have, for example, this term is, okay, why we have this n factorial is following. So, for example, this is a so-called Y group of UN. Okay. So Y group means that, okay, so originally we have n eigenvalues, but of course I just wrote x1 to xn, but of course we can just change the, order of eigenvalue. For example, even if you say x2, x1, x3, etc., so everything is same. So then we have a kind of the change of invariance under the permutation. So this is just a factor by this n factorial, which is interpreted as a so-called wide group of unitary group. Okay, so then the final part, so this is actually integral over the eigenvectors, but actually this gives you just a volume of UN. So in this context, actually the integrand can be written only in terms of the eigenvalues, eigenvalues. And then actually the eigenvector dependence is only the last part. So then in that context, after this separation variable, eigenvalue part, eigenvector parts, which are completely separated. And then the eigenvector parts basically plays no role. So then we can now focus on this eigenvalue parts, which is integral over the x. Okay, so then typically in the context of matrix model, so okay, originally we have origin as integral over the matrices, but typically we only consider this integral of, okay, so-called eigenvalue integral system. Eigenvalue integral system. Okay, so then maybe, okay, I didn't write about this delta. This delta is so-called Vandermonde determinant. Something like this. This is called a Vandermonde determinant. So from this expression, it's not so much trivial, but actually this factor is written as a determinant. So this is also the reason why actually related to the fact that this comes as a Jacobian. So Jacobian is actually coming from the determinant of change of variable, etc. So then actually, so this delta part has an interpretation as a Jacobian in this context. Okay. So then we are interested in this kind of integral, which is n variable integral. But okay, so then what we are interested in this context. Okay, of course, if you can evaluate this integral explicitly, of course, it's very nice. But typically, so we're interested in some statistical behavior or corrective mode behavior of these eigenvalues. Of course, just n equal 1, so this is one variable integral, so then everything is fine. But typically, so we are then interested in behavior or asymptotic behavior in Lagian situation. So what is okay, so this is analogous to the taking a thermodynamic limit of, say, physical system. So then we are interested in, okay, so then we want to study this Raj and limit of this system. This is a thermodynamic limit. Thermodynamic limit. Okay. Okay, so then for this purpose, okay, so what we can do. So actually the observation is following. So for example, we have, okay, so this is a bit artificial, but for example, we have just looking at integrand. So we have a factor n here. So in this context, if you think about the situation where this n is very large, so actually, so we may apply the, so for integrand becomes having a very sharp peak. So in this context, actually, we can apply that approximation, which is called a steepest descent or the saddle point approximation. So this is one of the reasons why we choose this kind of peculiar, normalization of potential. But actually, so this is our primary interest here. So then, okay, so let's discuss this Radian behavior with the so-called Coulomb gas approach. Coulomb gas picture. What is this? Okay, so now we have an integral over this eigenvalues, but let's rewrite this patron function in the following way. So this z is, of course, we have a several constant term, but it doesn't matter in this context. Of course, originally we have any variable integral, but just rewrite some. Okay, formula just like this. So what is this S function? So where this S of X is called the action functional, or said effective potential. So this is given by point. Then interaction term. Okay. Okay, so I think it's clear why we have this kind of structure. The first term is corresponding to the just originality, so trace term, potential term. But in addition, we now also have a logarithmic interaction term, which comes from the actual Jacobian part, this van der Monde term. Okay. So then the picture here is that, okay, so then this is the reason why this approach or this picture is called a Coulomb gas picture, in a sense that we originally have a potential of this some gas, but in addition to this, so we have some interaction between particles. So then, so in that sense, this now problem is now converted to the many particle system with interaction between them. Okay. So then basically this is a so this is a potential term. So this is a kind of interaction. Okay. Of course, this is slightly different from the standard Coulomb interaction. So Coulomb interaction in a 3D is, one over R interaction. But actually, this kind of log type Coulomb, actually, if you go to the lower dimensional situation, actually the Coulomb interaction becomes logarithmic. So in this context, actually, this log interaction is directly interpreted as Coulomb gas Coulomb interaction in a lower dimension. In this case, actually, the 2D. Right. Okay. So then let me give the one quick comment here. So then this is also related to why we put grand and big N in front of the potential function V. The reason is the following. So now, for example, starting from, okay, looking at the first term, so this is N contributions. So then in that context, actually this term, okay, this term contributes as ON. Roughly speaking, we have N terms, so then we have ON. On the other hand, so this term, so we have roughly N squared contribution because this logarithmic interaction, this is a summation over I and J, which is a double sum. So then in that context, summation is a double sum over N. So then this gives you the N squared contribution. But at the same time, so we have a factor 1 over N here. So then, okay, so then so we have actually basically similar, compatible contribution from the potential term, the interaction term. So then in total, so we have ON contributions. So this is the reason why we put a big N in front of the potential term. So this for this purpose, actually we can we have a compensation between the potential term and then the logarithmic interaction term between the particles. So actually, so this this compensation gives us a very interesting physics in the end. Okay. So then another comment here is that, okay, so then going back to this partition function as an integral over this minus ns. So this is quite analogous to the actually path integral. So this is also the reason why we use this kind of terminology, in the sense that this S actually plays a role of the action function in this zero-dimensional quantum field theory system. Okay, so then from this point of view, so if you take, okay, so Rajan limit here, what's going on? So then this is again so analogous to the path integral formalism. But if you take Rajan limit, so actually this integral actually is localized to the some classical path, classical configuration. Okay, let's denote something like this. Okay, so this is okay. So, but in this context, actually this n is n plays a role of the 1 over Planck constant. Okay, so just compared to the standard path integral formalism, if you write this kind of path integral, so we have a coefficient h Planck constant. So for example, this here, so this is replaced with 1 over h bar. So then, so we have essentially the path integral expression. But in this context, actually n plays a role of the 1 over h bar. So then taking n to be very large, so this corresponds to the h bar to be very small. So this is actually the analogous to the classical limit, how to get the classical mechanics from this path integral formalism. Originally, so in a quantum system, so we should take into account all the configuration summation, but in a classical limit, we can only focus on the classical path. So actually this classical path now corresponds to the somehow, okay, some is obtained by the equation of motion in this context. Okay. So this is actually another, way to see why this matrix integral is interpreted as dimensional reduction of this quantum field theory. Of course, we don't have a derivative term, etc. So then, but we still have a very analogous structure to the quantum field theory. Okay. So then the question is that, okay, so now we have nice this kind of picture. So then the question here is that, okay, so then what kind of configuration dominates in the Rajan limit? So for this purpose, let's study the so-called critical point. Okay, the critical point. Which means that basically the solution to this equation of motion in this context. So let's denote this critical point configuration as follows. Okay, let me use this kind of shorthand notation. But this means that this ds is basically total derivative. And more explicitly, so because s is a function of n eigenvalues, n variables, so then this ds is a sum of h derivatives, dxr. Okay, so then ds critical point is actually the stationary point with respect to this action functional. So then, moreover, so we already know what is the explicit form of this action functional. So then we can compute explicitly what is derivatives here. So now, okay, so now we have just derivative minus 2j except for I minus 2 here. So we already have an explicit form of this action functional. So then how to get this critical point is very easy. Just, okay, so see this here. First is, of course, contribution from the potential, and the second is a contribution from the interaction. Okay, so then we have this kind of equation for every eigenvalues. But okay, so then actually we can solve or we can nicely characterize this equation by introducing an auxiliary function. So then, okay, I just give you the result. lemma. So actually this ds equals 0 equation, basically this equation motion or solution equation motion. This condition is equivalent to the following equation with respect to some auxiliary function. 1 over n minus px, where this wx is an auxiliary function defined like this, and also p function is looks similar but slightly different. Something like this. Actually, this critical point equation is equivalent to the differential equation with respect to this auxiliary function, which is given by w, and also this p. And one quick remark here is that okay, following, of course, okay, looking at this expression, it looks like especially this w function may have many pole singularities, because of course, if you put x equal xi, of course, we hit the pole singularity here. Actually, so this w function is actually singular at the point of eigenvalues. Okay, so then from this point of view, we have a similar structure for p function, but on the p function side, actually all these pole singularities are cancelled between this with this contribution from the numerator. So then on the other hand, this p is regular. So then this implies that this p is actually a polynomial function in x. So then another remark is that, okay, so w doesn't depend on the choice of potential p function, but this p function depends on the choice of this b function, which is a potential function. So then let's call this equation for w by this star equation. And then we have a several remark here. So then one remark here is that actually this star equation is a differential equation with respect to w, which is furthermore nonlinear, because the first term is the w squared, second time is the w derivative. So in that sense, this is actually a nonlinear differential equation for this w function. But actually, this is even nonlinear differential equation, but actually this kind of nonlinear differential equation is actually classified as a so-called Riccati type ODE. So okay, I will come back to this issue later, but actually for this Riccati type nonlinear differential equation, actually there's a nice way to linearize this nonlinear ODE. So then after that, so we actually rewrite this ODE in terms of just as just a linear differential equation. Okay, so this kind of rewriting is very essential for the later purpose, but okay, I will come back to this issue later. Okay. Okay, so then we have this kind of differential equation. But one remark here is that in this differential equation, so we have, for example, n dependence here. So from this point of view, actually, so moreover, we are interested in large n limit. So in this context, if you have 1 over n here, so we expect that this term doesn't contribute in this limit. So then, especially in the large n limit, so we have a following statement. So especially in the large n limit and to infinity, so this critical point equation, the star equation, is equivalent to the just algebraic equation, because we originally have a differential, but this differential term is suppressed in the larger limit. So then the remaining is just w squared, w, etc. This is actually the algebraic equation. I mean, having no different derivatives. So the more precisely, so in a sense that this ds equals 0 is equivalent to some algebraic function. Get this at the Lagian xy equal to 0. But okay, for simplicity, just denote w as y here. So what is this h function is a point? So h of xy. Just to rewrite in this star equation in the Lagian regime, but y squared minus y plus p of x. So it's clear that in the Lagian limit, so there's no derivative term with respect to w. But on the other hand, so this potential term, so this is actually we determine or we choose some specific v function. So this is actually input data. And then at the same time, we also have a p function, but the p function also depends on the v. So in that sense, the p is also interpreted as input data in this context. So then having, choosing some what kind of potential you think about for matrix model, we have this algebraic equation here. So then, so then we have this kind of algebraic equation. Then, so we can conclude that, so we are interested in ds equals 0, but moreover, it's a family of this. So this is actually xy equals 0. So actually, so if you define this as sigma, so this is nothing but the algebraic curve, so which presented before. So this is, which is called the, actually, in this case, it's called a spectral curve. Of the matrix model. Spectral curve. So because so we are as I said, so this critical equation, say equation motion, is equivalent to the zero locus of this algebraic function h. But we are interested in a family of this critical equation, critical points. So because we are interested in the generic solution of equation motion. In this context, it's natural to think of the set of these solutions. And actually, set of this solution actually defines the set of this zero locus algebraic function, which is nothing but the algebraic curve in this case. And then this algebraic curve appearing here in the Lagian limit of this matrix model is in this context called the spectral curve of this matrix model. So then, this is a first connection to the geometric object starting from the matrix model. And then moreover, one remark here is that, actually, so this algebraic function h is a degree 2 for y variable. And actually, in this case, actually, the sigma is hyperelliptic. Hyperelliptic curve. Because degree of y in this h function is just a degree 2. Okay, so then from this point of view, so we can get a hyperelliptic curve in the Lagian limit of this matrix model. Okay, so then very nice. Now we have this kind of geometric object from the Lagian analysis of this matrix model. But then question is, from this geometric object, what we can discuss or what we can get the physical information, like what is the physical quantity, etc., from this geometric object. That I'm going to tell you next. Okay, maybe we can take a small break, like a few minutes. Spectral curve. Okay, so then let me start. And then a question concerning connection between spectral theorem and the spectral curve. Actually, so the auxiliary function that I introduced, I think W function here. So actually, this is called a resolvent. So the reason is that I think this is an expression in terms of the eigenvalues, but if you write this in terms of matrix, it's more clear in the sense that this W is okay, maybe because this W is written as 1 over n or trace of x minus m here. Okay, right. So that in this context, this resolvent is defined only defined on a complex plane except the spectrum of this matrix M. So in this context, actually, so from this auxiliary function, resolvent function, actually we can extract the information about this spectrum, say, basically this distribution of eigenvalues of this matrix. Yeah, I will come back to this issue more concretely. So how to get the information of eigenvalue distribution using this auxiliary function, which is a resolvent. Okay. Any other question? Okay. Okay. So then, okay. So then we now have this algebraic object, which appear from the Lajan analysis of this matrix model. So then next, let's discuss how to get some physical information, or say some statistical information of these eigenvalues, like distribution of eigenvalues, etc. So, okay, let's think about some example, example, which is so-called a double wave potential. So which is, very roughly this potential function, v of x is given by whatever, say t2 of tx squared, and then a t4 x degree 4. Of course, if you want, you can add degree 1, degree 3, but let's just take this situation. So in this case, for example, we have a potential function takes this kind of form because this is degree 4. Of course, this also depends on the sign of T2. But for example, we can derive this kind of double wave potential by tuning the coupling constants. Okay. So then from this potential function, so what we expect for the distribution of eigenvalue, say this spectrum of the situation. So as I said, in this matrix model picture or Coulomb gas picture, so we have potential of, potential for each particles, charged particles, but we also have an interaction, say a repulsive interaction between the particles. So then what we expect is that, so we have this kind of distribution for these particles because we have two local minima. So we expect that, the several particles are just localized on the left well, the others are localized on the right well, for example. So this is what we expect from this picture. And then the reason why we have it broad widths for distribution is that, if we don't have interaction between them, we just expect only all the particles are just localized on the just really local mean. But now we have interaction between the particles, so then we expect a bit broad distribution of these eigenvalues. So this is the reason why I draw this kind of configuration. Okay. So then, so now this is just a very big picture. But now, let us translate this into the distribution of eigenvalues. So as I said, so we have so this was a really schematic picture. So then more precisely, so we expect distribution of eigenvalues like this. So then bottom is actually the X plane. So this is actually now, okay, so for several reasons, so we now think about this. Originally, these eigenvalues are real numbers, but for the latter purpose, let's think, okay, we now think about the eigenvalue distribution in a complex plane. So this is better for several reasons. So then we think about this kind of distribution of eigenvalues here. Okay. So then, okay, then originally we have n eigenvalues, but from this picture, so we expect that okay, n1 eigenvalues are on left, n2 eigenvalues are on right. But of course, we have a constraint like n equal n1 plus n2. Total number should be fixed. So then from this picture, okay, and then the question is that, okay, so this is also related to the previous question, which is from this, how to extract the information of a spectrum from this auxiliary function, which we call the resolvent function. Actually, the resolvent function, as we saw, so this is actually the singular at the point of the where we have eigenvalues. So then actually, so this is related to the singular structure of this spectral curve. Okay, how to interpret this? So because originally this spectral curve is a degree 2 algebraic equation. So in that sense, okay, so if you solve this h equals 0 equation, so we have two solutions corresponding to the, okay, so just recalling formula of second degree algebraic equation, we have a square root, but depending on the sign of square root, we have two solutions basically. And then the two solutions are converted to each other through this singularity. So we, from this point of view, we have another copy of this structure. So then we have so idea is the following. So now at the finite n, so we have finite number of eigenvalues. But if you take a large n limits, so all these pole singularities are actually condensed to the cut singularity in this of this resolvent function. So then this orange domain actually here. So this condensation of eigenvalues are promoted to the cut singularities. So then in this context, actually, so corresponding to the each local minima, so we have a cut singularity of this, for this resolvent function. So that's why I'm now having two seeds, and then which are connected to these cut singularities. So then from these cut singularities, actually, so if, okay, so this is, okay, we need a bit of several steps, but just give you the final picture. Actually, so in the context of such kind of complex function, so we can compactify the complex plane by adding the infinity, etc. to, okay. So then after having this kind of compactification argument, actually this two-cut solution is topologically converted to the so-called genus 1 Riemann surface, which is basically the torus. So this is a genus 1 and genus 1 surface. So topologically, this left configuration is equivalent to the genus 1 Riemann surface here. Okay. Okay, then so then, for example, the how to read off physical quantity, say the distribution of eigenvalue, etc. Okay, so then now let's take this kind of process here. So which means that okay, let's think about the counter integral along this A cycle of this W function, dx. So why we consider this? Because this W function has a pole, okay, just a recording definition of this W function here. So this has basically the union of this okay, sorry, connection is not good. Okay, sorry. I think note is not moving on your side, right?
I can see everything normal.
Okay, so displaying in double web. Okay. Okay, so is it now? Okay, sorry. Sorry, just a second. Maybe on my side, connection of iPad is okay. Okay, so let's start. So then what I'm saying here is the following. So considering this double wave potential, we have this kind of distribution or configuration of singularity of the poles, and concerning this resultant function. Then let's think about this counter integral of the double function along this A cycle. The motivation here is the following. So because this double function was defined like this, so then this has a pole singularity as a place of this eigenvalues. So then if you think about the counter integral around each eigenvalues, actually we can count the eigenvalues, residue 1. So then actually, so from this point of view, we can say that this counter integral of this A, counter A actually gives you yes, n over n1. So 1 over n is just a normalization of this resultant function, but actually surrounding this A cycle. So because around, okay, inside this A cycle, we have n1 eigenvalues. So then just considering counter integrals, we can count number of eigenvalues inside this A cycle, which is now n1. Okay. So typically, so we define the epsilon1 here like this. So which is called a filling fraction. Yes. And then apparently, so we have another possibility, which is the counter surrounding the N2, I mean, other side of the well. But actually, due to the constraint, which is N equal N1 plus N2, so then the opposite side doesn't give it further information. Only this A cycle, if you determine the A cycle, the other side of cycle is automatically fixed by this total number conservation situation. So, okay, so we can similarly define epsilon2. But this can be fixed by the constraint like n equal n1 plus n2. So which is equivalent to 1 equal epsilon1 plus epsilon2. Okay, so then this constraint is more clear in this this Riemann surface picture, because this A cycle integral is corresponding to the integral along this cycle, non-trivial cycle in this genus 1 surface. So actually, if you want to think about another cycle around surrounding N2 eigenvalues, so we have a cycle, but essentially this is the same, so topologically. So then in this context, we have only one non-trivial cycle along this direction. Okay, so this topological point of view, of course, we have one more cycle, but in this context, for example, this is, okay, now this is A cycle. So we have another cycle going this. So then original picture, this is related to the cycle. Sorry for this same color. But, so this is called the B cycle. So this also gives you the some very important information. But, okay. So anyway, the point here is that okay, from this geometric picture, so we can extract the information about the distribution of eigenvalues, how many eigenvalues there, etc. So in that sense, actually, this epsilon actually parameterizes a configuration of this vacuum. Vacuum means that the solution of equation motion. So then actually, so this filling fraction in general, okay, so this is, in this case, we already have a, one non-trivial filling fraction, but in general, we have many filling function for the more complicated situations. In this case, actually filling fraction actually parameterize the vacuum configuration. So more, mathematical language, this is, okay, so this is in turn, we can say that this epsilon parameterizes a modular space of vacua. In other words, this epsilon is interpreted as coordinate of modular space of vacua in this context. Actually, so we will see the very similar structure in the context of supersymmetric theory, say suborbital theory. Actually, so in the context of suborbital theory, we have very similar structure. So having, okay, I will return to this issue, but having a suborbital curve as an algebraic curve. So then we have a non-trivial cycle around this suborbital curve, like A cycle, B cycle. And then actually the A cycle integration gives you the some parameter, which is analogous to filling function. And it turns out this filling fraction-like object plays a very important role as a coordinate of a modular space of vacua in the supersymmetric case theory. So then the structure is very analogous. So actually matrix model is a really baby version, but it still has a very interesting connection to this kind of problem. Okay. Okay, so then, okay, this is okay, how to get information about the distribution eigenvalues from this geometric object. So then, okay, then the question is, okay, so, okay, as mentioned before, okay, this is a rare just only classical setup. So then the next question is how to see the quantization from this geometric object. Okay. Then next step is a quantization. Quantization of, say, modular space. So modular space is in general, so the some parameter space of the some solution to some equation, typically the algebraic equation or differential equation. So from this point of view, I'm not using this sense of the word like modular space, but this is just a family parameter space of solution to equation motion in this context. Okay, so then, okay, how to see this quantization from our point of view? So then, proportion here is a following. So actually, starting point is again a Riccati equation that we introduced before. Here, star equation here. Okay. So this, as I said, this is actually non-linear differential equation, but actually, so this is classified into the so-called Riccati type equation. So then, actually, we can linearize this differential equation. So then the statement is the following. So actually the star equation is actually linearized. Follows, say, and then P contribution. So then what is this psi function? Actually, so in this context, we derive this auxiliary function W in terms of this psi function as follows. This is log derivative of psi. If you want, this is just psi prime over psi. Okay, so just to recall in, I think the first year, the OD course, for example, how to linearize this Riccati equation is following. So just rewriting this W function as a ratio of, for example, psi prime and psi. So then actually the resulting differential equation for this psi function is actually a linear differential equation. So in this case, actually, this is a degree 2 differential equation. Essentially, actually, this is ODE. And then moreover, the structure appearing here. So in this context, we have, okay, we can see this equation as, okay, now we have psi function, but something acting on psi function, then 0. So that means that some differential operator acting on psi function. So then from this point of view, we can reinterpret, namely, so we have a more nice sophisticated expression like x hat, y hat, acting on this psi function equal to 0, where this x hat is just a multiplication of x variable, and then y hat here is a difference operator here, obeying. Okay, x hat, y hat, commutation relation is now 1/n. 1/n. Okay. So the actual h function is really the h function that I introduced before. Okay, if you remember this h function here, h function is y squared minus p prime y plus p of x. So this is a function of y and x. Then I just put in a y, y hat, which is actually a differential operator. So then actually, so this part is, of course, this y hat squared. So then this part is, okay, we have this is a y hat, and then a p of x of adjusted. So then actually, thinking of the operator analog of this h function, so actually this is nothing but a differential operator acting on this psi function. Say, let's call this psi function wave function. Because this second order differential equation is very little in the forms of the Schrödinger equation. So then, okay, the remark here is that, okay, so hence, so this Schrödinger type equation, ODE, this is called actually the quantum curve associated to this matrix model. Okay. So, okay, the Schrödinger, reason why I'm saying the Schrödinger type is that, of course, in order to have a genuine Schrödinger equation, so we should be careful about the sign of second order differential or imaginarity, etc. But formally, so now, actually 1/n plays a role of the IH verb. So then in this context, so I'm just saying this Schrödinger type ODE. But anyway, so this what I'm saying here is that originally we are interested in this Radian limit of saddle point equation, critical equation. But just rewriting this differential equation in terms of this psi function, so we can linearize this thing, and then which actually turns out to be the just this Schrödinger type ODE, and then which is nicely written in terms of some differential operator acting on this psi function, which is basically the wave function in this context. Okay, so then, okay, so from this point of view, of course, this classical limit. Classical situation is 1/n to 0 limit, because now just compared to the standard canonical quantization scheme, 1/n plays a role of the Planck constant. So in that sense, 1/n to 0 means a classical limit. Now there was, of course, n to infinity limit. On the other hand, the quantum situation, in this context, we are now, we want to interpret 1/n to be the non-zero, finite, but still it's better to think about this as a small parameter, because in the standard, for example, quantum mechanics scheme, so for example, if we want to apply the perturbation expansion of this system, for example, so then typically we assume that the Planck constant is sufficiently small. So in this context, let's think about 1/n finite. but still assume that the 1 over n is sufficiently small. Because recording the origin of this star equation, so this is a critical point equation. Of course, in order that this saddle point approximation or this kind of analysis works well, so we assume that the Planck constant is sufficiently small. So this is another reason why we assume 1 over n is finite, but still sufficiently small. So then in this context, for example, we can apply a perturbation scheme with 1 over n parameter. So then in this context, so perturbation theory with respect to Planck constant, which is 1 over n, is actually the expansion of, say, physical quantity with respect to 1 over n parameter. So this is a analogous structure for this matrix model. So then the perturbation with Planck constant is now translated to the 1 over n expansion of this system. Okay, anyway, so then having a finite n, so we have some quantum structure from this. And then let us discuss another some quantum perspective at a finite n. Okay, the another perspective is that, for example, the cycle integral at finite n. So the cycle integral means that, so we introduced the quantum integral of this W function. So say, let's rewrite 2 pi I over aj. Okay, in general, so let's think about more general Riemann surface. So, so first let me write this. This is epsilon j, called nj. And so in general, so we have, if you have a more complicated potential, we have more possible filling functions. So the more geometrically, so this A means foreign. So we have several higher genus in general. So A cycle is, for example, A1, A2, AG. So then at this moment, so we have several cycle integrals, but from the matrix model interpretation, so each quantum integral along this A cycle actually gives us information about how many eigenvalues are distributed to each local minima. Okay. But the interpretation here is, so this is fine, but the interpretation here is that, so from this point of view, we can see that AJ, just rewriting, is actually, this means that the 2 pi I n times some integer value. Okay, so why we have this kind of rewriting is that, so actually this is quite analogous to the so-called Bauer-Sommerfeld quantization of quantum integral, or say, a cycle integral over the phase space of the classical integral, classical mechanics. So just say, or Sommerfeld quantization with the unit 2 pi I n. So just recalling what's this Sommerfeld quantization. So this is, if you think about the quantum integral in phase space of classical system. So typically, so this W dx is replaced with P dx, for example, momentum, etc. And then Bauer-Sommerfeld quantization condition is that this kind of quantum integral is quantized with a unit Planck constant. But compared to this Bauer-Sommerfeld quantization to our case, so now actually this unit is now 2 pi I over n, which is of course consistent with our interpretation, like 1 over n plays a role of a Planck constant. Okay, so in that context, okay, finite n, so we can count the eigenvalues, for example, 1, 2, etc. But of course, if you take the Lagian limits, so this n to infinity, so we still have some number, but this is now approximated to the continuous parameter in the Lagian limit. But at the finite n, actually, we can count how many eigenvalues, etc. So this is actually nothing but a quantization, Boas-Zumwalt quantization in this context. Lagian, so we cannot, we can just say that, okay, how many, we can just think about the ratio. We cannot count because number of the eigenvalues are now infinite. But if you think about the finite n situation, we can count the number of fluxes, or say number of this kind of the unit. Actually, so this is a quantization from this point of view. Okay, so this is another perspective why this finite n configuration is corresponding to the quantized situation. Okay, so this is okay from this point of view. From Lagian, so we have a classical system, but if you take into account the finite n connection, we can, this system is now translated to the quantum mechanical system. So this is a quantization of geometry, which naturally appears from the study of this matrix model. Okay. Okay, so then we have studied this quantization picture of this geometric perspective. So then, next I want to explain in several the first talk is how to see, okay, now this is a geometric side, but then what is the algebraic side of this story? Okay. So then let's think about some algebraic side of this story. Okay, so then how to see some algebraic structure from this matrix integral. So from this point of view, so let's think about some symmetry of this partition function. So why we need to see symmetry in order to discuss algebra is, okay, the big picture is the following. So if you have a symmetry of system, so typically we use a language like the Lie group or something, group theory, to describe the symmetry, because the symmetry is rephrased as an invariance under some transformation operation. So in order to describe this transformation, so it's nice to use a language group theory. And then if you have a group, for example, Lie group, typically a continuous group, if you have a group, Lie group, so we can think about the Lie algebra, which is corresponding to the infinitesimal version of this transformation. So then from this point of view, in order to discuss algebraic structure, so it's nice to think about the symmetry of the system. So this is typical illustration. Okay, so then how to discuss the symmetry partition function? Of course, we have already discussed the, for example, unitary group invariance of this matrix, but actually it turns out that we have more big symmetry from this matrix integral. There's a point. So then before going to matrix, just to give you the one example. So for example, just one variable integral. For example, we have dx of fx. But actually, so we can change the variable, integral variable, like x to y, like this, dx, dy. So then this is x of y or something. Of course, in general, so integral, okay, first of all, we have integral over x, but if you introduce another variable, which is connected to the y, x, which is y, new variable y. So of course, we can derive the integral as integral over the y, of course. But ultimately, this kind of invariance is actually ultimately related to the diffeomorphism. Diffeomorphism, which is associated to the variable change x to y. Of course, this is a one variable case. Okay, it's very simple enough. But the question is it possible to do the similar thing for the matrix integral? So this is a question. matrix analog. Okay. So then if you think about the analogous transformation, and then analogous, if you have an invariance under the similar transformation at the matrix level, so we can discuss something, okay, analogous to the different morphism in this context. So then let's think about the change of variable. Change of variable at the matrix model. So let's think about n to the, sorry, small change of, okay, the notation is here. Now k is bigger than -1. Okay, k plus 1 is just a notation. And this, of course, this is now, this is a epsilon is now supposed to be very small. So then this transformation is now infinitesimal. The decimal transformation. This is also related to the, okay, what I said, in the sense that if you think about infinitesimal transformation, we can directly see the algebraic structure, which is corresponding to maybe Lie group or other, sorry, Lie algebra rather than Lie group. Okay, so then let's think about this kind of change of variable, then how this partition function behaves. Okay, so then under this transformation, so this partition function originally given as an integral over exponential trace of E of n. Okay, so for simplicity, we don't have n here. Okay, this is just to simplify the following argument. So the following argument, so we don't need a big n here. Okay, so then under this transformation, so this behaves like, okay, the original part, and then all the epsilon term is given like this. Is m to l k minus l minus trace, so sorry, trace of m k plus 1 b prime. Yes. So under this transform, of course, we have a higher order, but we don't think about this. So the idea, okay, so the idea of this computation is, okay, first term, two terms are corresponding to the actually the measure term. This comes from the deviation of the with respect to measure, and this comes from the actually the potential term. Yeah. Okay. So then, okay, so under this variable change, we have this kind of contribution. But then now, if you assume this invariance under this infinitesimal change of variable, actually we can get some non-trivial relation among correlation functions, actually. Invariance, and this transformation, this deformation, say. Actually, so we can get okay, some non-trivial relation among between the correlation function of the following form: k minus l minus trace so where this is some average of some operator of some function m is given like dm exponential minus trace of O of n. So this is basically the notation for this average in general, this correlation function. Okay. So this means that, okay, imposing this invariance and this infinitesimal change of variable deformation, actually we can get a non-trivial relation between the correlation functions. And let's go, this is a two-star equation. And actually in the context of, okay, as I have emphasized several times, so actually this matrix model is interpreted as zero-dimensional quantum field theory. And actually, so this is zero-dimensional analog of the Schrödinger-Dyson equation, if you want. Schrödinger-Dyson equation can be obtained from, for example, path integral formalism, and then a change of variable, so then imposing the invariance, so then we get a non-trivial relation between the correlation functions. Actually, this is a baby version of the Schrödinger-Dyson equation, actually. Okay. Okay, so then from this, okay, now we have a several non-trivial symmetry. So then the relation between the correlation functions. And then, final few minutes, I want to discuss how to get some algebraic structure from this picture. Okay, for this case, so actually, so we need a bit of preparation, but okay, let's introduce operator formalism. What is this? So the recording operator formalism is following. So how to interpret this correlation function, say Schrödinger-Dyson equation. So actually recording this trace of U here is sum of k equal 0, 3, 9, formally 1, t, k, k. So actually recording this structure, actually this Tn of z. What's going on? Because original projection function is depends on the choice of potential function, but the potential function of course depends on this choice of Tn, which is a coupling constant. In this context, of course, projection function is a function of this coupling constant. So then what's going on? Here, of course, now just thinking of derivative with respect to this coupling constant, minus trace here. But now this trace of Vm is given like this. So then actually we have minus n of n exponential trace of u here. And actually this is nothing but, okay, we have the 1 over n factor, but this is nothing but the correlation function, say, moment, like this. So from this point of view, actually the correlation function is nicely given by the derivative with respect to projection function. So hence, so we have somehow the correspondence trace of n is something like minus n here. Of course, this is analogous to the standard approach of the quantum field theory. So if in order to compute the correlation function in the path integral formalism, so we think of some generative function. So once you can compute the generative function, or correlation function can be obtained by just applying a derivative, etc. So this is quite analogous here. And then moreover, so this is actually also interpreted as a Fourier transform because we have exponential trace here. But each trace we have Tn trace mk. So then we have exponential something times something. So this takes a very analogous to the Fourier kernel in the Fourier transform. So, okay, anyway, so this is just a detail, but in general, so we can apply this, considering a derivative with respect to coupling constant, we can actually think about a very generic correlation functions. Okay, so then, let me give them one more operator. So then let's, definition. So we define following operators. So then an, just a short, essentially this Tn, etc. But it's better to introduce this kind of normalization for these operators. So this is square root of Tn. So we define this and 0. So then which obeys actually in this notation, this an, am obeys n delta n plus m0. Okay. So this is nothing but a Heisenberg harmonic oscillator. So then with we also define a vacuum state, which is that some an 0 equal to 0, and also dual vacuum. So idea is that now A positive is actually given by the derivative. So then if you apply this to some constant function, so it's going to be 0. So in that sense, a vacuum is interpreted as some constant function with respect to Tn. And then we can similarly define a dual vacuum. Okay. So then, okay, using this kind of notation, actually, we can get the following statement. So we had a Schwinger-Dyson equation, but in terms of this operator, so we can rewrite nicely this Schwinger-Dyson equation, which is called Virasoro constraint. Okay, so then the statement is following. This Schwinger-Dyson equation denoted by double star is rewritten as follows. So just acting some operator Lk to Z equal to 0, where this K is now bigger than 1. And then this Lk is now rewritten in terms of the combination of An, etc. So where Lk C A sorry, this is here. And moreover, this Lk obeying Lk prime here. So this is called a Virasoro algebraic structure. Okay, precisely speaking, so we should introduce a notion of this dot symbol, but this is called a normal ordering. So we should impose a specific ordering, but after imposing properly, actually this Schwinger-Dyson equation is written as using a Virasoro generator here. So this is called this Schwinger-Dyson equation here written is called a Virasoro constraint actually. So then this Virasoro, okay, so then the appearance of this Virasoro algebra is very interesting because this Virasoro algebra is known to be the symmetry algebra of two-dimensional conformal field theory. So in this sense, actually this quantum algebraic structure in this case is actually nicely characterized by this Virasoro algebra. Yes, because the reason why this is called this is interpreted as a quantum algebra is that okay. So just okay, let me conclude a few words. So we have in general Virasoro algebra. Say Virasoro generated by Lk. Originally, this is a general here. And in general, this Lk, okay. Okay, the first part is same, but in general, we have a non-trivial additional contribution. K square minus 1, K plus K prime equals 0. And the reason why we don't have this C term in the previous expression is that, okay, the previously, so LK is only defined for the K, okay, K bigger than -1. So actually, in order to have a non-trivial C contribution final term here, actually, so we need to prepare the K -2, etc. So in this context, the matrix model picture, so we only have half of bilateral algebra, but in general, we can extend this construction to get a full bilateral algebra. Okay, and actually the one final comment here is that actually this subalgebra structure of this bilateral is actually, we can extract SL2, which is L0, L plus -1. Actually, so we can check that just considering L0, L plus 1, L minus 1, this actually gives you the SL2 algebra, which is a subalgebra. Actually, in general, so bilateral algebra is, okay, one of the algebraic characterization of bilateral algebra is actually infinite dimensional extension of SL2 algebra. Of course, SL2 is a very standard finite dimensional algebra, which is very known. But actually, bilateral algebra is actually extension of this. More say, catchy thing is, okay, if you want, so you can say bilateral algebra is a quantum extension or quantum version of SL2 algebra. Actually, so we have several expression, interpretation as a conformal group or extension, especially in the 2 dimension, etc. Okay. So, okay, so then I think let me stop here. The final thing is that, okay, so we have discussed a matrix model and then the Lagian limits. So we have some geometric picture. So then, so if you think about the finite end connection, so we can actually discuss a quantum correction, so which serves as a quantum geometric picture. And then on the other hand, so starting from this matrix integral, so we can construct some algebraic, infinite dimensional algebraic structure, which is nicely described as the bilateral algebra. So actually, so this bilateral algebra is now interpreted as some quantum algebraic structure appearing from the matrix model. Okay. Okay, so let me stop the first talk. Thank you for your attention.